So let's start our next section, which is 13.10, and it's about Lagrange multipliers. So I kind of want to start this section with a goal. And what is our goal or our focus for this section? What we want to do is we want to find maximum and minimum values of a function of more than one variable. So let's say of two variables, say the function f, two variables, subject to a constraint curve. It's going to be given by g of xy equals some constant c. Now this is similar to what you did back in like Calculus 1, where you were doing optimization problems. It's similar idea, but now we're talking about functions of more than one variable. So the first thing we're going to mention is something called Lagrange's theorem. And so Lagrange's theorem says let f and g have continuous first partial derivatives such that f has an extremum at a point x naught, y naught on the smooth constraint curve g of xy equals c if the gradient of g at my point is not equal to the zero vector, then there is a real number gamma such that, or sorry, lambda such that the gradient of f equals lambda times the gradient of g at my point. So I'll say that this theorem, it doesn't tell you how to find extremum, how to find maximums and minimums, but it tells you where you can look. You can look, and in particular, it's really this equation right here that tells you where to look for extremum. So we're going to break this down into a method that we can apply here, what will be called the method of Lagrange multipliers. So I'll say to find the maximum, a minimum, or maximum of f subject to the constraint g of xy equals c, we're going to follow this procedure. So the first step, you're going to simultaneously solve the equations, the gradient of f equals lambda times the gradient of g, and your constraint equation, g of xy equals c. So if you're simultaneously solving equations, what that means is you're going to solve a system of equations, So from this first equation here, you're going to get fx equals lambda gx, partial derivative with respect to x has to be the same. The I and j component of your equation, or the I components have to be the same, and then your j components. And then you also need your constraint equation from here. So g of xy equals c. So you're solving this system of equations right here. And then what you're going to do after that is you're going to evaluate f at each solution obtained in the previous step. The greatest value yields the maximum of f, and the least value yields the minimum of f, subject to the constraint g of xy equals c. So now that we have this procedure, we're going to look at some examples where we put this into practice.